Welcome to review lecture for Chapter 2, Physics 111, One-Dimensional Motion. Upon successful completion of this, you should be able to correctly answer questions and problems related to distance, displacement, speed, velocity, acceleration, and reference frames. Okay, we're somewhat familiar with speed and distance and velocity, but you're familiar with it in ways that are what I call civilian ways. Now you're going to be learning it using the formal language of physics. Okay, now motion is something we're all kind of familiar with, some of us more than others, and we start studying motion at a very young age. You watch a 2-year-old getting up and tripping over his own feet and falling down, or you watch him sitting in a high chair and he's dropping things off the high chair and watching him hit the ground, or he throws a ball across the room, right? He is actually learning physics, and you all had to learn to drive. You had to learn physics of how to start and stop a car. You had to understand how to judge speed and distance and velocity and acceleration, and it took some time to do that, and you had to practice. And guess what? You still had to practice. Now, the motion in physics is called mechanics, and motion is just a change in position. We always make measurements of position, distance, speed with respect to a reference frame. Now, a lot of times this is just implied. The ground is the reference frame, the Earth's ground, but that's not always true. A choice of a reference frame can either simplify or make your problem impossible to solve. So it's one of those things you have to learn how to do. And the choice of reference frame is yours. There's only one real warning here, and that is you have to make sure your reference frame does not accelerate. Now, that is actually special relativity, believe it or not. Einstein's theory of special relativity. You cannot have an accelerating reference frame. If you do have an accelerating reference frame, you have to go to general relativity, which is way beyond what we're going to cover in this class. So make sure your frame does not accelerate. Now, acceleration is any change in speed or direction. So if you're going around a curve, you're accelerating. Now, you can walk down an aisle on a speeding train. Your speed with respect to the train is much different than that with respect to the ground. Also depend on which direction you're walking. So suppose you're on a train that's traveling at 100 kilometers per hour to the east. You're walking toward the front of the train at 4 kilometers per hour with respect to the train. See, so that's the reference frame. What is your speed with respect to the ground? Okay, well, you're going in the same direction as the train. Okay, toward the front of the train, assuming the train is traveling forwards. And 100 plus 4 kilometers per hour equals 104 kilometers per hour. You probably can do this in your head. Now, suppose you turn around and you walk toward the rear of the train. What is your speed with respect to the ground? Well, it's 100 minus 4 because you're going against the train's motion, kilometers per hour, and it's 96 kilometers per hour. So the reference frame makes a difference here. And also the direction of your speed with respect to the train and the ground. So all of that matters. You have to be very precise in physics about your language. And there's a difference between distance and displacement. They're two different things. Distance is measured using the actual path. So in the picture below, an object travels 70 meters in one direction, then turns around and travels 30 meters in the opposite direction. This is the dashed line here. That's what this object actually did in terms of what an odometer would read. So the dashed line is a scalar. It has magnitude only. It shows the distance traveled by the object. And the distance is 70 meters plus 30 meters for a total of 100 meters. Displacement is how far the object is actually from the starting point. Notice that's different than this. It's the straight line distance. It's the smallest distance. So object travels 70 meters to the right, which is a vector, and then travels 30 meters to the left, which is another vector. The blue lines are vectors right here. They have magnitude and direction. They show the displacement. We're going to assume, assuming right is positive. Now, we didn't have to do that. We could make left positive too. It doesn't make any difference. Just have to pick one. Don't change the middle of the problem. You got 70 meters plus or minus 30 meters because this one's going to the left. You have displaced 40 meters to the right. The magnitude of the displacement is always less than or equal to the distance. Displacement is the straight line distance that you've traveled from the beginning to the end. So displacement is change in position, and we can say that as delta x, and that'd be x final minus x initial. Remember, it's always final minus initial. It could be x2 minus x1. The delta just means a change in something. The sign depends upon the direction with respect to the reference frame, and what you decide is positive. Now, the choice of the frame is up to you. Don't change the frame in the middle of the problem, and make sure the frame does not accelerate. It's okay if it moves at a constant velocity. In other words, constant speed at straight line. The displacement in here, this direction is positive. It's going from 1 to 2. It's going in the positive x direction. This is negative. It's going from 30 to 10 to, 30 to 10, it's going in the negative x direction. This one was going from 10 to 30 in the positive x direction. So this would be positive 20 meters, and this would be negative 20 meters. Now, speed is a scalar, has magnitude, not direction. Speed is the distance traveled per unit time, and you're all familiar with this, 40 miles an hour, 30 kilometers per second. Here's your speedometer. The speedometer measures speedometer. Look at the word. You're familiar, you're allowed to go 70 miles an hour on the freeway, right? The average speed is the total distance traveled divided by the total time. Now, if you take a very tiny time interval, then you have the instantaneous speed. This is what the speedometer or a cop's radar gun measures. So speedometer actually is a speedometer. It measures speed and it measures instantaneous speed. Now, velocity is a vector which has both magnitude and direction. Where speed's a scalar, velocity is a vector. Velocity is the displacement per unit time in a certain direction, like 70 miles an hour north. It's displacement divided by elapsed time. The average velocity is the total displacement divided by the total time. That includes the direction because it's a vector. And that would be total displacement divided by elapsed time. So V average will be delta x divided by delta t. Now, a lot of times you leave off the deltas on some of these. It gets kind of a pain in the butt to write them. Okay, sometimes you might see them implied in things. You might also see as a derivative a dx dt. Okay, if you've had calculus, you would see dx dt. That's basically all the same thing. Okay, now, you guys don't need to know calculus, but if you do know calculus, your life will be slightly easier. And the units on this, of course, are meters per second, feet per second, miles per hour, kilometers per hour, and there are other units too. Of course, this just means some sort of change, final minus initial by definition. So V average is x final minus x initial divided by t final minus t initial, or x minus x naught divided by t minus t naught. Now, a lot of times we set this equal to 0. We set x0 equal to 0. Okay, and a lot of times, and many times, we set t0 equal to 0. Okay, in which case, then we have V average equals x over t. Remember, I told you sometimes we drop the delta off. This is the more familiar form. But in this case, you got to remember t is the elapsed time and x is the displacement covered in that time. The instantaneous velocities, the limit as delta t goes to 0. So very tiny time intervals that you're measuring this over, take them down to 0. And that would mean the limit of delta x divided by delta t. Okay, now the V average is d divided by t in a certain direction. Of course, this is a vector. I can't put arrows over this because PowerPoint doesn't really do that very well. It just moves them all over the page. So rather than do that, I just bolded it. And I'll just tell you whether it's a vector or not. And here it says in a certain direction, that means it's a vector. And of course, d is the displacement in that direction. That means it's a vector. Constant velocity is, you probably guessed, a constant speed, a steady speed. Driving on highway with cruise control. An object can have constant speed without constant velocity. An object cannot have constant velocity without constant speed. So when you travel in a circle, your direction is changing. If anything changes, either the speed or the direction changes, it's an acceleration. So traveling in a circle is not constant velocity. Carousel travels at a constant speed, but not constant velocity. Because the direction of the carousel, all these horses on here are constantly changing direction. As they go around, they're going in a different direction. So when you go around a freeway curve, okay, even if you keep the accelerator, the speed is 70 miles an hour, you go around a big curve, you are actually accelerating. Now, you are actually accelerating toward the center of the curve, and we call that centripetal, center-seeking acceleration. That's a subject, I think, for chapter 3 or 4, if I remember correctly. So that's sort of a look ahead, so be warned, that's coming. So change in velocity, if either the speed or the direction changes, or both, then you have a change in the velocity, and that is called an acceleration. It's kind of the opposite of constant velocity, and any falling object demonstrates changing velocity. It goes faster and faster as it falls. Any object moving in a curve demonstrates a changing velocity, even if the speed is constant. And we call this acceleration. Okay, acceleration is delta v over delta t. It's the change in velocity divided by elapsed time in meters per second squared or feet per second squared, usually. The average acceleration is a vector. That equals the final velocity minus initial velocity divided by the elapsed time. The average acceleration as a scalar equals final speed minus initial speed divided by elapsed time. Now notice there's no neat little word that's different here, okay? You just have to know which is a vector and which is a scalar from the problem. The average acceleration is v minus v naught divided by delta t, or delta v over delta t. You might, if you've had calculus, you're probably familiar with dv dt, derivative. If you haven't had calculus, don't worry about that. The delta, or the d, is the final minus the initial by definition. Now, a lot of times we drop the delta on time and call it elapsed time. We can also make it start from 0, in which case it's just v over t. So it might be written different ways. Acceleration can be a vector or a scalar depending on how it's calculated or defined. A vector acceleration can occur when the speed and or direction changes. Deceleration, the direction of the acceleration or the direction of A is opposite to that of the velocity or displacement, otherwise known as braking. It's not necessarily the same as negative acceleration. Negative acceleration, the direction of the acceleration is opposite to that of the defined positive direction of the reference frame. That is not necessarily deceleration. Instantaneous acceleration is A equals the limit as delta t goes to 0, delta v over delta t. So in other words, you're taking a very tiny time interval. Acceleration, of course, is the rate of change of velocity. And here I've got some examples here. Here's an example of positive acceleration. A is in the same direction as the defined positive x. But we define x as positive to the right, and that's the choice of our reference frame. That's part of our reference frame choosing. And in this case, at time t equals 0, the car is stopped. Maybe it'll stop light, and the light turns green. The driver presses the accelerator. And the acceleration is 15 kilometers per hour per second. It's kind of a mixed unit, but in reality, it should be not a mixed unit, but it's good enough for this. After 1 second, his speed has increased to 15 kilometers per hour. And you can see that by just multiplying 1 second times this. After 2 seconds, he's up to 30 kilometers per hour. That's 2 times the acceleration. After 5 seconds, he's 5 times 15, which is 75 kilometers per hour. Notice this vector is increasing all the time. That's what acceleration does. It increases the speed. Acceleration is constant, but the speed is increasing. And so this image shows a negative acceleration. A is opposite to the positive defined direction for the reference frame. It also shows a deceleration. The direction of A is opposite to V, where the object speed is decreasing with time. In other words, this guy's braking. The sign on A is negative in this case because A is opposite to the positive x direction. The speed is decreasing with time. So here at time t equals 0, the car is going 15 meters per second. He sees a red light up ahead. He hits the brakes. His acceleration is minus 2 meters per second squared. And after 5 seconds, he's down to 5 meters per second. Where do you get that? Okay, 2 times 5 is 10. And that'll be minus 10 because it's minus 2. And you subtract that from the original speed, 15. You end up with 5. We'll show you equations for calculating this, but you have to understand how to apply the equations. You can't just memorize it. Okay, here's another example. Here we have a positive direction. Remember I told you can pick positive direction any way you want. I decided to make it toward the left. And what's going on here is the car starts at T1 and V1 at minus 15 meters per second. Why is this minus? Because this velocity is in the negative direction as defined by this. So there's a minus sign in front of this. The acceleration, he's hitting the brakes. Okay, the acceleration is opposite to the initial velocity. And so it's in the positive direction because it's in the same direction as the positive direction is defined in the reference frame. So this is a deceleration. A is opposite to V. That means he's braking, but the acceleration is positive as defined by the reference frame. The speed is still decreasing with time because the direction of A is opposite to that of V. So this is braking. Now here we have the positive direction directed to the left, and this is at time t equals 0, V1 equals 5 meters per second, and he sees that the light up ahead, which was red, turns green. So he says, okay, I want to get through that light, so I'm going to press on the accelerator. And I'm going to accelerate at 2 meters per second squared. And after 5 seconds, you take 5 times 2, that's 10 meters per second, plus the original 5 meters per second gives you 15. So we'll show you how to do this. Don't get too panicky with this. I'm just showing you this as examples. The acceleration is positive because it's in the same direction as the reference frame's positive. A and V are in the same direction. And V is also positive because it happens to also be in that positive direction. And since A and V are in the same direction, the speed is increasing with time, and it's shown that by the larger arrow here. For what we were talking about before, these were all constant accelerations. For constant acceleration, otherwise known as uniform acceleration, you can use something called the kinematics equations. This means that acceleration is not allowed to change with time. It has to be constant. If the acceleration is changing with time, you cannot use these equations. So there's a whole bunch of them here, okay? And I won't go over every single one of them. You are welcome to look at these. Now, notice that these symbols might be different than the ones in the book. Everybody uses different symbols. Some people use D, some people use S, some people use other things, X, some people use delta X. They use all these different symbols, okay? And there's nothing I can do about that. You have to get the feel of the equations. Other texts will use different symbols and often switch even in the same text. Many use S for distance and or displacement. In practice, I don't like, because that gets it confused with the units seconds. You know, all of these things have meters per second. You get that confused with this or that. If this is an S, it gets very confusing. Now, these are good things to write on your cheat sheets for tests and homework. Put these in your notes. Again, used to handling these things. And I'm going to show you how to pick which one you're supposed to use. You have to pick these out, okay, to which one you're going to use in a problem. So the only way you can get that is to actually do your homework. Now, again, I cannot warn you enough. Don't use these for anything but constant acceleration. For anything that's non-constant, you have to use something else, either calculus, which would be physics 211, way beyond the scope of this course, or conservation of energy, which we will cover later. And if you can use conservation of energy, use that, okay? Because then you don't have to worry about things like direction or anything else like that. It's because energy is a scalar, so it's a lot easier to handle. Remember, you still have the quadratic equation. Now, if you look at this one right here, if you rewrite this to move the d over to this side, you wind up with something that looks like this. I might have a negative sign in here. That doesn't matter. So the solutions of this, the roots of this, has two possible roots. T equals minus the quantity, b plus the square root of b squared minus 4ac all divided by 2a. The other root is t equals minus b minus square root of b squared minus 4ac all divided by 2a. This can be used to solve for t in some of the kinematics motions equations. Now, usually only one of these solutions will make sense from a physics standpoint. So this means you have to understand the physics. You cannot just blindly plug numbers into an equation or into a calculator. You also have to think. You also have to understand physics. So in other words, it's the old saying, you got to do your homework. So constant acceleration is defined as a equals v minus v naught over t. For constant acceleration, the average velocity of an object during a time interval t is v average equals x minus x naught over t minus t naught. Or you might write that as x minus x naught over t, or just x over t. If x0 and t0 are 0, we can drop them out. V average is equal to v plus v naught over 2. Okay, so this would be the initial velocity. This is the final one. You can combine these two equations, and you wind up with x equals x naught plus v naught t plus 1/2 at squared. You can recombine and eliminate t. You can say v squared equals v naught squared plus 2a times the quantity x minus x naught. And you can also use conservation of energy to derive the same equation. We'll do that later. Again, these can only be used at constant acceleration, also called uniform acceleration. Anything else, you're going to need calculus or conservation of energy, which is chapter 5. If the acceleration is constant, the average a equals the instantaneous a. And then you can use these for motion at constant velocity. Constant velocity means the acceleration is 0. And then they just become really easy by just dropping out all the a's. The a's go away. So here's some other ways they wrote this equation, and what is the information? This velocity is a function of time, displacement is a function of time, velocity is a function of displacement. And if, in other words, if you have this is along the x-axis, you can also have it along the y-axis by just replacing x with y. That's all you have to do. And now we're all familiar with gravity. Gravity is an acceleration. Okay, and Einstein's general theory of relativity says it's pretty much an acceleration just like any other acceleration. And it is just a very common acceleration. We just give it the special symbol g, but you can treat it like any other acceleration. And on Earth, gravity is 9.80 meters per second squared, or 32.2 feet per second squared. So this means on Earth, when you drop an object, as you let go of it, of course, it starts from 0 speed because you're holding it. When you let go of it, at that instant, the speed is 0 and it hasn't gone anywhere, 0 feet per second. Okay, after 1 second, it is accelerated at this rate, 9.80 meters per second squared. After 1 second, it's going 9.8 meters per second, or 32.2 feet per second. After 2 seconds, you multiply 2 times this, you get 19.60. If you multiply 2 times that, you get 64.4. meters per second and feet per second, respectively. After 3 seconds, 3 times 9.8 means 29.4 meters per second. 3 times 32.2 feet per second is 96.6 feet per second, etc. 4 seconds, 4 times 9.8 gives you 39.20 meters per second. 4 times 32.2 feet per second squared, 128.8 feet per second, etc. Now, in reality, on Earth, air resistance would eventually put a stop to the acceleration, but get air resistance out of your head. Okay, I'm going to say that again. Get air resistance out of your head. 99.9% of the time, we neglect air resistance. People always want to put the air resistance in. Okay, please don't do that. Air resistance is basically fluid flow, and it's a drag force. It's proportional to the square of the speed of the object. It's rather complicated, and in this class, we don't cover it because that's a topic for fluids, and that is a 300 level engineering class, which is way beyond what we do in here. If there's anything to do with air resistance in a problem, they'll tell you the force of the air resistance is so many newtons. Okay, you're not going to have to calculate it. They'll just tell it to you. Now, air resistance can be very confusing. It's one of those things that people live with all their lives, and they don't realize how much it affects everything. So, for instance, you're dropping a ball, say a baseball, and a sheet of paper, and you all know what happens when you do that. The ball hits the ground long before the sheet of paper does. And everybody thinks that this is accelerating more than that. The gravity does not operate the same on these two objects. It actually does. Because if you crumple up the sheet of paper, the two will hit the ground at the same time. Because what happens is air resistance is proportional to the area, okay, that this is trying to go through this cross-sectional area here. Yeah, when you crumple it down, you reduce the area, so you reduce the drag force. We talk about forces, talk more about that in another chapter. Okay, and if you take it, for instance, a rock and a feather, you drop them in an air-filled tube, the rock will hit the ground long before the feather does, but if you take all the air out of the two will hit the ground at the same time. This was actually done on the moon during the moon landings. My father worked for the space program, and he helped get us to the moon. If anybody ever dares to suggest that we didn't go to the moon, they have to answer to me, because I know we went to the moon. I lived through this. This was a very famous experiment. They took the Apollo astronauts, took a falcon feather, because I think the mission was named Falcon something, if I remember correctly, and a hammer, okay, a hammer, head off a hammer. And he dropped the two objects from the same height, and they hit the ground at the same time, because here's the hammerhead, here's the feather, and this cloud here is basically the regolith, which is the powder. The surface of the moon is covered with something called regolith. It's the powdered remains of millions of little meteorites that have bombarded the face of the moon. All of it's basically 4 billion year life. These two hit the ground at the same time. Mass and weight have nothing to do with how fast something falls. Just say that again. Mass and weight have nothing to do with how fast something falls. Having a massive object dropped in a vacuum from the same height as a light, not massive one, will hit the ground at the same speed at the same time as the light one. Any difference is due to air resistance, not mass. So in other words, the drag force of air. So in vacuum, you'd have no trouble with this concept, because you wouldn't be worrying about air resistance. So in this class, remember, you're usually doing this in vacuum. So you're not doing this in air, but you are doing it in a gravity field. So what happens when you toss a ball up into the air? You all have done this. You try to toss it straight up in the air. What's it do? It goes up to a certain height, pauses, and then comes back down. What is the acceleration on the ball when it's rising? It's going up. Now, most people that haven't had physics would say it's up. They've got velocity and acceleration confused. The velocity's up. The acceleration is down. The acceleration due to the gravity is always down toward the center of the gravitating body. In fact, if you drop an object off a tall building, don't do that. You drop an object and you could extend the line of that motion, it would go right through the center of the Earth. So you can actually determine where the center of the Earth is. You do that a couple places and do a triangulation, you can find the center of the Earth. So at any rate, why? Because G is down toward the center of the gravitating body. And we're going to later find out it exerts a force, a gravitational force on the object, and the acceleration of the force have to have the same direction. And that's toward the center of the gravitating body. Okay, so what's A on the ball when it's rising? G down. What's A on the ball at the top? It stops for a motion at the top, for an instant at the top. But that doesn't mean the acceleration's gone away. If the acceleration were zero at the top, it would stay there. it would not come back down because that acceleration is caused by a force and the force is pulling the ball down. That's what makes it come down. Otherwise, it would stay there, just stop. The answer is G down. What's G on the ball as it falls? Most people don't have any trouble with that one. It's G down. So the whole free flight, this is called free flight. The whole free flight is G down. The acceleration is down toward the center of the gravitating body. Always down toward the center of the gravitating body. Don't forget that. People make mistakes in these problems by assuming G is up here and 0 there and down there. No, it's down through the entire flight. And you can use the kinematics equation by substituting G for A, but watch your signs. You got to set up your reference frame. What's up? Is up positive or down positive? You can pick. And you want, of course, you might want to use Y instead of X to sort of make it a little easier, but you don't have to. There's no reason you can't make this X. You can do it any way you want. Now, a body which is only under the influence of gravity, and that's what it usually is in this class, is in free flight or free fall. So rise and fall, how fast? Notice we're throwing a ball up in the air, and it rises and comes back down. So let's look at this. This is an experiment we've done. We start at 0 seconds and we launch the ball, throw it up or launch it somehow, straight up into the air. Time, 0 seconds, hasn't gone anywhere yet. We started with an initial velocity up at 29.4 meters per second, and the acceleration is G down. The gravity, the center of the earth is down here somewhere off the screen. So it's 9.8 meters per second squared down. After 1 second, the ball, and we'll show you later how to calculate this distance, okay, so don't worry about that yet. After 1 second, the ball is 24.5 meters up in the air. The velocity now has dropped by 9.8 meters per second because that's the acceleration down. So it's decelerating. So the velocity, you subtract 9.8 from 29.4, you end up with 19.6 after 1 second. But the acceleration's still down because nobody turned off the gravity. Gravity doesn't get turned off in this class unless I tell you it is. After 2 seconds, the ball has gotten up to 39.2 meters of altitude above the ground. The velocity now, you subtract 9.8 meters per second from this, you end up with 9.8 meters per second. The velocity is lowered to 9.8 meters per second, but it's still up, still rising, but it's slowing down. Acceleration is still down at 9.8 meters per second squared because nobody turned off the gravity. At 3 seconds, it reaches the top of its flight. It is now at an altitude of 44.1 meters. The velocity is 0 because it's paused at that top of the flight. But nobody turned off the gravity. If they do turn off the gravity, it'll just sit there. The rest of this table would go away, and this would be 0. But it's not 0, so it's still directed downward. So at this instant, the ball is reversing direction. It's going to fall down. Instead of falling up, it's going to fall down. After 4 seconds, it is now down to 39.2 meters altitude, and it has accelerated downward, as it's been doing all along. It's been accelerating downward, 9.8 meters per second down, because this is still 9.8 meters per second squared down. After 5 seconds, it is down, the height has dropped to 24.5 meters. The velocity is increased to 19.6 meters per second down, and it's still got the same acceleration because nobody's turned off the gravity of Earth. After 6 seconds, it has reached the ground again, so it's come back down to where it started from, and it hits the ground, smacks into the ground at 29.4 meters per second, but the acceleration is still 9.8 meters per second squared. Now notice something here. There is a symmetry here. If you look at 0 seconds and 6 seconds, notice the numbers are the same. The only thing different between 0 seconds and 6 seconds is the direction on the velocity. If you look at 1 second and 5 seconds, the numbers are the same. The only difference, again, is the direction of the velocity. 2 seconds is like 4 seconds. That's the way free flight is. When you throw a ball straight up in the air and it reverses, you can use half the flight. So you can use the fact that there's a symmetry here. You don't have to analyze the whole flight if you don't want to. You can just analyze half of it. Now, sometimes you may have heard G-force, okay, and there's actually a ride called G-force. Yeah, okay, now sometimes to give accelerations in terms of G's, like when astronauts are launched or when you're going on a ride, or you're a fighter pilot, They talk about how many G's they have to withstand. 1G is 1 Earth G, and that is 9.8 meters per second squared or 32.2 feet per second squared. So that's the definition of a G. Velocity and the resulting displacement are always in the same direction. So these are some notes on direction. It gets very confusing after a while. But notice the acceleration does not have to be in the same direction as the velocity or displacement. So go back to that ball in the first half of its flight. Velocity is up, but where's the acceleration? Down. Why is this going on? The ball's rising, the acceleration is down, G's always down, and the ball's slowing down because these are in the opposite direction. The acceleration is in the same direction as the change in velocity. So the change in velocity is downward as the ball is rising. Final is smaller than the initial. Final minus initial is negative, so it's downward. If you define up positive, gravity is always down toward the center of the gravitating body. The choice of reference frame should also include a choice for positive direction in the x and y axis. Okay, so sign conventions. The devil is in the details on these things. Okay, pick a zero position of positive direction for displacement. You have to pick a reference frame. Put the coordinate axis at the 0 and indicate the positive direction for x and y. And you can pick anything you want as long as x and y are perpendicular to each other. Velocity is positive when it's in the same direction as the positive direction for displacement. Pick a direction for positive acceleration. It's a good idea to make it in the same direction as positive displacement. It makes it a little easier. Now, later we'll specify the direction of the force causing the acceleration and the direction of the acceleration must be the same. And this is when we talk about chapter 4, we talk about forces. Because what actually causes acceleration is a force. Problem solving. I can't emphasize reading the problem thoroughly. No tricky stuff. Decide on a time interval in the objects you're considering. Draw a sketch. Choose coordinate axes and positive directions. Write down the knowns, that is the given with units, and the unknowns, which is what you want to find, and preferably with the units. And as I've mentioned before, any kind of unknowns, which are what you want to know. So what is the problem asking for? What is the physics of the problem? Is it a constant acceleration problem? Is the acceleration 0? These things, this means you can use kinematics. If it isn't constant acceleration, you're going to have to do something else. Okay, if the acceleration is 0, the A will be 0 in all the kinematics equations. You can make them easier. You want to look at the equations and pick those that include both the knowns and unknowns. Do the equations fit the physics? Are they valid? You cannot use kinematics equations for non-constant acceleration. You need calculus or conservation of energy or some other way of getting it. You can solve the equations. You should do them using the symbols. Reduce it to a single equation by substitution. You have what you want on the left-hand side of the equal sign. Everything else as simple as possible on the right-hand side of the equal sign. Now notice you plug the numbers in at this point. Most people do this out of order, and when they do this out of order, they screw up. Okay, plug the numbers in at the end, not at the beginning. Okay, so figure out what equation you're supposed to use. Solve the equation, simplify the equation as much as possible, then stick the numbers in. And people leave the units off. Don't leave the units off, put them in. Make sure they come out correctly, because if the units don't work, you will not get the right answer, and I will put units traps on test questions. Okay, then you notice the calculation is step number 9. It's not step number 1 or 2. Students in this class inevitably make the mistake of doing this completely backwards. They do this part first. They ignore these steps, and they go right to these. And then they come to me and they ask me, why don't I get the right answer? And I say, okay, show me your work. And inevitably, I see this kind of bad stuff first. Okay, don't do that first. I had to sit there, hey, how do we do this in class? So now you do the calculations. Then once you get it, doesn't make sense, doesn't seem reasonable. And you should also always reread the problem. Did I answer the question? You'd be surprised at how many people on a test, they'll probably ask them for velocity, they'll answer acceleration or displacement instead of velocity because they don't read the problem. Okay, did you answer the question? Have you answered the question that was asked in the problem? And are the units okay? And by the way, when you're doing homework, this is also good for your homework problems too. If you get into the habit of doing it this way, and I'll show you some examples of that in a few minutes, if you get into that habit, it's a good habit. This way works. None of the other ways do. There are examples and more in the rough notes for the chapter. The rough notes can be found on Blackboard in the same folder as the lecture PDFs. And if you do look at any kind of problems elsewhere, you can also look at Sean's outlines and stuff like that. You should always try to work the problems on your own. You should you cover up the solution, work the problem, then check to see if you got it right. Do this in your notebook because then you have that work with you. You can take it with you on exams. It's easy to go back and refer to it. Before class, you should also answer all the checkpoints for yourself, work any of the problems that are in the lecture notes, do them for yourself. Then when you get to class, it's a low stakes assessment and you check to see if your answers are correct. So it's a self-assessment. If you get a whole bunch of them correct, you probably know the material. If you missed a bunch of them, you need to go back and review. If you do these steps along with reading the topics in the book, doing your web assigned homework for the chapter, those will help you properly prepare for the class. Remember, the lecture is the review. It's not the first time you see the material. If it's the first time you've seen the material, you're going to be sitting there going, I don't understand any of this, right? And you don't want that to happen. You want to be able to understand it and just have to fill in the little things that you don't understand, rather than I don't understand any of this, and you're left with this impossible task of filling everything in. That won't work. So here's some examples. Some of these should be done at home. When driving at 90 kilometers per hour, how far do you travel in 1 second? Well, write down what you know. The average velocity is 90 kilometers per hour. The time is 1 second. The unknown is delta x. Now, this is a constant speed problem. There's no acceleration. We can use kinematics because the acceleration is 0. It's constant at 0. So kinematics is okay. And we can pick a kinematics equation. And one of the ones I noticed here, I want delta x. I have v average. I have t. So here's one that will work. Delta x equals v average times time. 90 kilometers per hour times 1 second. Now, if I stopped here, I would wind up with something weird. I would wind up with 90 kilometers seconds per hour. I would know the units were wrong, and there would be a wrong answer on the test question that would give you 90 kilometers seconds per hour. That would be a wrong answer on a test question, and I guarantee somebody would pick that because they didn't do the units. You had to fix the units. 1 hour for 3,600 seconds times 1,000 meters per 1 kilometer. You do all of this, you end up being 25 meters. Now, this is why you don't want to drink and drive or do anything else which slows your reaction time when you're behind the wheel. So think about this. You're 90 kilometers per hour. That's about 50 miles an hour. In 1 second, you travel 80 feet. Now, if you are texting or doing anything else that pulls your attention away from the road, a lot can happen in 1 second. A deer can run out in front of your car. The deer can run right in front of you, and if you were not paying attention, you would hit him. Now, Milwaukee is 120 miles, air miles, due west of Grand Rapids, so this is a vector. Maria drives 255 miles in 4.75 hours from Grand Rapids to Milwaukee around Lake Michigan because she can't swim. What is her average driving speed and what's her average travel velocity? Now, of course, the speed is going to be different than the velocity here. Why? Well, notice that this is a displacement. This is a distance. The speed is the distance divided by the time. The velocity is the displacement divided by the time. The velocity will be less than or equal to the speed, the average speed. Okay, so you write down everything you know. Path length, distance, that's distance. 255 miles, that's what the odometer would read. The trip odometer, time is 4.75 hours. The displacement, which is what a GPS would tell you, is 121 miles. The unknowns are speed and velocity. Physics of this. Well, constant speed, kinematics problems, distance is greater than displacement, so speed will be greater than the magnitude of the velocity. It's just what I just said a minute ago. So the average speed is distance divided by time. And of course, you rewrite that in formula form as V average equals delta x over t, or you might just see x over t, 255 miles divided by 4.75 hours. This is 53.7 miles per hour. This is the average speed on her speedometer. Now, the average velocity is displacement divided by time. And displacement would be 121 miles, and that would be delta x, and t would be 4.75 hours. So V average, it's 121 miles divided by 4.75 hours, or 25.5 miles per hour west. It has to have a direction because it is a vector. Now notice that the magnitude of this is greater than the magnitude of that. And that's because the magnitude of this is greater than the magnitude of that. So average velocity is less than average speed because displacement is less than distance as expected. So see, here's a check. Do these checks. And the units came out. Example, a rocket lifting off from Earth has an average acceleration of 44.0 feet per second squared. Assuming it goes straight up, how far up does it go in the first 5 seconds? Okay, write down the knowns. The acceleration is 44 feet per second squared. We're going to assume it's constant. The initial speed, initial velocity is 0 feet per second. The time is 5 seconds. We want to know how far up. We're going to call up y direction, and this is a constant acceleration problem, so we can use kinematics for this. Set up a coordinate system. Up is positive, the ground is at y equals 0. We pick a kinematics equation that has the knowns and unknown, and we're going to write it in terms of y. Delta y, or y, is v0t plus a t squared plus 2. How do I know to use this equation? Well, I'm given a, I'm given t, I know v0, and I want this. That's that simple. It's like a recipe. An equation is just a recipe. Does the recipe get you what you want? Do you have the ingredients? Here are the ingredients. They're the ingredients. Now, you might have to turn this around. You can write equations differently, but it's kind of, in this term, it's kind of like a little recipe in a way. Okay, so 0 feet per second for v0 times 5 seconds. Of course, that one drops out. The acceleration is 44 feet per second. We have 5 seconds, quantity squared divided by 2. Now, notice the units. The second squared is going to cancel out that second squared, and it's going to wind up with 550 feet. So the units check says it's right, and it looks okay. A bullet is fired vertically upward from a gun and reaches a height of 7,000 feet. What is the initial velocity? How long does it take to reach the maximum height? How long is it in flight? And what's its velocity when it hits the ground? First thing you want to do is write down the knowns and unknowns, and I assumed that the sig figs were 3 sig figs here. Okay, that's usually a pretty good assumption. So delta y equals 7,000 feet, and the underline here is for that. And the acceleration is minus 32.2 feet per second squared. Up is positive, and g equals g all the way through the flight. The physics of this is a constant acceleration gravity problem. We can use kinematics because it's constant acceleration, and of course, as usual, we ignore air resistance. And we also know at the top of the flight, the bullet will pause at the top of the flight, and v at the top of the flight is going to be 0 feet per second. Now, the unknown, we don't know v0. Okay, so we want to look at the upward part of the flight. Then we can divide the flight up, just like we did with a ball, throwing the ball up and then coming back down. You can just take the first half, you can take the second half, or you can take the whole thing. You pick parts of the flight that you know something about. We know the top of the flight at 0, and we want to know what it is in the beginning. So we're going to look at the upper part of the flight. We're going to pick a kinematics equation that has the knowns and unknowns. And I look around. I want this. I know v at the top is 0. That's this. I want this. I know this, and I know that. I'm going to have to rewrite this. I'm going to have to turn it around. But it's still, all the ingredients are there. And everything I need, and it gives me what I want. Solve this for the unknown. Do it this way. Don't plug the numbers in here. Do it this way. V naught equals the square root of v squared minus 2a delta y. Now, notice that this will drop out, and you'll wind up with v naught equals minus 2a delta y, and take the square root of that quantity. Now, you have to be careful with signs here. Somebody's probably screaming, you can't take the square root of a negative sign. Well, it's okay because the gravity's negative because of the choice of the reference frame. Okay, so at any rate, we have the square root of this. Of course, 0 drops away. Minus 2 times a negative 32.2. That makes this okay. Times a 700 feet, and you're going to take the square root of the whole thing. Now, you notice that this will wind up as feet squared per second squared. You take the square root of feet squared per second squared, you end up with feet per second. So the units came out correctly. That's 671 feet per second. Now, that is the initial velocity, and if you look at the whole flight, as it comes back down, remember I talked about that with that ball, you threw the ball up, and there was like a symmetry between the upper part of the flight and the downward part of the flight. The speed going up is going to be the same as it is coming back down. Okay, so this will be 671 feet per second up. Part D will be 671 feet per second coming back down. This is why you should never fire a bullet into the air. Please don't do that. So this is just repeating this. Now we want to know, how long does it take to reach its maximum height? We know that delta y equals 7,000 feet. We know the acceleration is minus 32.2 feet per second squared, and I've considered up positive. That's g throughout the flight. We're ignoring air resistance. We know v top equals 0 at the top of the flight. We want to know the time. Again, it's a constant acceleration kinematics problem. We pick a kinematics equation that has all of these things in it. We know v naught, we know a, and we know v. We can solve this for t. T equals v top minus v naught divided by a. And of course, v top is 0. We could have dropped that out here if we need to. And minus 671 feet per second divided by negative 32.2 feet per second squared. Okay, so it ends up being 20.8 seconds, and that's the answer to part B. So the time it takes to rise to the top exactly equals the time it takes to come back down. So this is 1/2 of the total flight. So you just multiply that by 2 to get the answer to part C. Now, you could have very easily picked the whole flight. There's no reason you couldn't do that. I just decided to do this. For D, we've kind of already answered this before, but just to prove that it works. Okay, so for this, V equals V naught plus AT, you look at the second half of the flight. For this part, V naught equals 0 feet per second, and time equals 20.8 seconds. That's the time it takes the bullet fall from the top of its flight and hit the ground. So V equals V 0 feet per second plus a negative 32.2 feet per second squared because gravity's down, and 20.8 seconds, and that equals minus 670 feet per second. The difference between this and the one we had before, the previous page, is just due to round off. Don't worry about that last digit. And the negative sign means it's down. Okay, so that means the velocity is downward. Light plane must reach a speed of 30 meters per second for takeoff. How long must a one-ray be if the acceleration is 3 meters per second squared? Okay, you know the acceleration is 3 meters per second squared. V is 30 meters per second. It's going to take off, so the initial speed is 0. We need to know how long that runway has to be. That'll be delta x. We're going to assume the acceleration is constant. Then we can use kinematics for this. We pick a kinematic equation that contains the knowns and unknowns. Okay, well, we know V naught. We know the acceleration. We want to know delta x. We have 30 meters per second for the final speed. We have to rewrite this. Solve it for delta x. Delta x equals V minus V naught squared divided by 2a. And of course, one of these is 0. V naught 0, so it drops out. So it just becomes V squared over 2a. And by the way, if you have a thing like this again, you can have another problem like this where this V naught is 0, in which case you can go right to this step. As long as it matches the physics, you can reuse the equation. Constant acceleration and V naught 0, reuse this. Okay, so then you have 30 meters per second quantity squared divided by 2 times 3 meters per second squared. Units cancel out correctly, and you wind up with 1.5 times 10 to the 2 meters, or 150 meters. So he needs that runway to be at least 150 meters long. You know, when planes make that mistake, they try to take off when the runway's too short. Not pretty. A helicopter is ascending vertically with a speed of 5.5 meters per second when a package drops from it at an altitude of 105 meters. How much time does it take the package to hit the ground? And we know that the acceleration is g, and it's going to be minus 9.8 meters per second squared. We're calling up positive. V naught is 5.5 meters per second. Y equals 0 meters, and y 0 equals 105 meters. Of course, this is where it hits the ground. And delta y is 105 meters. So we need to know the unknown is the time. The physics of this is gravity again. We're going to let the coordinate system, the origin, be on the ground and up be positive, which I sort of picked here, but it's okay. Pick a kinematics equation containing the knowns and unknowns. We pick one. Delta y equals v naught t plus 1/2 at squared. Well, we know a. We want to know t. We know v naught, and we know delta y. We're going to have to rewrite this and put it in form of a quadratic equation, which is, of course, why I picked this problem. So 0 equals delta y plus v naught t plus 1/2 gt squared. At this point, this is one of the few times when I suggest that you plug in the knowns at this point, because sometimes things drop out. And it's a little harder to solve a quadratic equation using this thing than it is to get rid of some of this, so simplify some of this. One of the few times I suggest that you put the numbers in. So 0 equals 105 meters. That's a delta y, plus a v0, 5.5 meters per second t, plus a 1/2 times a negative 9.8 meters per second squared times t squared. And we can simplify this part right here and rewrite it in terms of 0 equals minus 4.9 meters per second squared times t squared plus 5.5 meters per second t plus 105 meters. At this point, you should check the units. Okay, t squared will be second squared, and that will cancel this second squared, so this comes out meters. This t will cancel that seconds, so that will come out meters, and so does that. They all have to come out the same. In this case, all meters. So then we are free to take the roots. We have two roots. One of them is t equals minus 5.5 plus the quantity, the square root of 5.5 squared minus 4 times 105 times a minus 4.9 divided by 2 times a minus 4.9, or 5.22 seconds. The other one is t equals minus 5.5 minus a quantity. It's the same thing with a minus sign instead. And it comes out minus 4.10 seconds. Now, this root will make sense. That one doesn't. This one would happen before the package actually fell out of the helicopter. So the positive root is the one that makes sense because the package was released at time t equals 0, so t equals 5.22 seconds. The other root doesn't make any sense. So that's when you have to understand the physics. Somebody who didn't understand the physics might pick this one instead. And of course, the incorrect answer would be on the test, would be either sitting there. That would be sitting there on the test. Okay, if the position of a truck is 0, what does the speed have to be 0? No, you pass a 0 mile marker on the freeway, You might be going 70 miles an hour. You can set the position to anything you want. That's a choice of the reference frame. If the velocity of the truck is zero, does the acceleration have to be zero? Nope. Think of what happens when you're sitting at a stoplight and the light turns green. You press on the accelerator. Your velocity is zero for an instant, but your acceleration isn't. And also, you can think of the ball at the top of its flight. Does the speedometer of a truck measure velocity or speed? It measures speed. What could you answer to measure velocity? GPS or a map. If the average velocity is non-zero over some time interval, does this mean that the instantaneous velocity is never zero during the time interval? No. You can stop at a light for a minute. You can make a pit stop. Okay, your average velocity would still be non-zero, but you would have a zero velocity while you're waiting at the light or you're in the pit stop. If the velocity of the truck is non-zero, that is v not equal to zero, can the acceleration of the truck be zero? Yeah. The truck is moving at a straight line at constant speed. When throwing a ball straight up, which of the following is true about its velocity, v, and its acceleration, a, at the highest point in the path? V equals zero, but a is not equal to zero. Nobody's going to turn off the gravity. That ball's not going to stay there. It's going to come back down. So that means the acceleration is not zero. You throw a ball straight up into the air. After it leaves your hand, at what point in its flight does it have the maximum value of acceleration? This is a trick question. It's in free flight. Acceleration is the same all through the flight. Constant equal to g down everywhere and everyone in that flight. Don't fall for this one. Al and Bob are at the top of a building. Al throws his ball downward. Bob simply drops his ball. Which ball has the greater acceleration after release? Trick question. They're in free flight. They've released the ball. They have the same acceleration. And you know what it is? G down. You throw a ball upward with initial speed of 10 meters per second. Assuming that there's no air resistance, the useless situation in this class, what is the speed when it returns to you? Well, it's in free flight. It's going to be coming down with the same speed that it left, 10 meters per second, only down instead of up. Al and Bob are at the top of a cliff of height h. Both throw a ball with initial speed v naught. Al throws his ball straight down. Bob throws his ball straight up. The speeds of the ball when they hit the ground are VA and VB. Neglecting the air resistance, which of this is true? Now, what you want to do with this is you want to break this thing up. Bob is throwing his ball straight up, and just ignore the rest of this down here. Just look at this part right here, right here. Okay, so he throws the ball straight up. It goes up to a certain height, pauses for an instant, comes back down, and when it passes the point where he threw it, the ball will be going at a same speed down because the flight is symmetrical. So if this leaves his hand at 20 meters per second, when it passes where his hand is, it's going to be going 20 meters per second down. That's exactly the same as this. So if this and this are the same, this and that will be the same. So these two are exactly the same. VA and VB are the same when they hit the ground. Okay, because this situation is exactly the same. Just ignoring this part. Okay, because remember, you can split the flight up. You don't have to do the whole thing. You can split it up. So VA and VB are the same. You drop a rock off a bridge. When the rock has fallen 10 meters, you drop a second rock. As the two rocks continue to fall, what happens to their velocities? Their accelerations are the same. The acceleration is the time rate of change of velocity. They will both increase at the same rate because they have the same acceleration. A car travels around a 10-kilometer long circular track, returning to the starting point in a quarter hour. What's the speed? Well, 10 kilometers divided by 0.25 hours is 40 kilometers per hour. What's the velocity? Velocity is displacement divided by time. It returned to the starting point. The displacement zero, velocity zero. So the speed is distance divided by time. 10 kilometers per point divided by 0.25 hours, 40 kilometers per hour. Velocity is displacement divided by time, and it's zero because displacement is zero. If it comes back to the starting point, the displacement is zero. So the displacement of a round trip is zero, no matter where you go. Thank you.